one of the techniques we use to practice related rates is using geometric shapes. Now, in practice, this does, in sort of like the real world, it does come into play, but in a lot of ways, the reason we do this is because we feel relatively safe with geometry. We've done it in multiple courses, not only geometry, but sometimes it's used in algebra and whatnot. And so it's a good introduction on how related rates work. But there's sort of an algorithmic approach for how you can go about geometric problems. And it doesn't always work out this easily, but this is sort of a baseline good idea. So what I'm going to do is if I have some sort of question about a geometric related rate, I'm going to write the equation of the relationship being described. So that might mean it's a volume equation, so I'll write the equation for volume. Or it might be surface area, so I write the surface area equation, something like that. And then the second thing that I'm supposed to do is differentiate both sides with respect to the same variable. What I mean by that is most of the time you're figuring out how one quantity is changing with respect to time as opposed to the other, but sometimes you'll see problems where you want to see how the area is changing with respect to the height or something like that. That can happen. It's not as common, but just make sure that whatever derivative you take, you're taking the same derivative on the left and the right-hand side of the equation. The third one is plugging in known information. And sometimes you need the equation from up here. And what that means is that you may have information about the side of a cube, and it might relate to its volume. You might be able to find the volume at that particular time. So don't forget that you always start off with an equation, so use that relationship and the relationship from the derivative together. And finally, we just simplify and solve. And let's do an example to kind of flesh this out. So if I have the radius of a circle, and it's changing at 6 centimeters per minute, so I have some circle, and it's growing. That radius is growing at 6 centimeters per minute, so it's expanding. Then we want to find the rate of change of the area when the radius is 38 centimeters. So what's interesting about this is you might wonder how is that related? Is it going to grow at the same rate? Is it going to grow at some odd rate? Are those relationships proportional? We don't know, and part of doing this helps us tease out those similarities. So the first thing we want to do is write the equation that makes sense. Well, we want to figure out how the area is changing. So and we know information about the radius. So how are the area and the radius of a circle related? Well, they're related by the classic formula. Area is pi r squared. Simple enough. Now the second thing is we want to differentiate both sides. Now this is changing some length with respect to time. So this makes sense that we would be doing a time derivative. So I'm going to take the derivative with respect to time of both sides. Now, this is pretty transparently dA dt. But over here, remember, if we were differentiating with respect to just r, like, forgetting that that's dt and thinking about if it was dr, we would use the power rule and we bring down 2 pi r, and then we would subtract 1 from the power, so squared becomes 1. And then, because it's a derivative with respect to t, we do dr dt. So now we have a relationship that relates the change of the area to some sort of jumble here, 2 pi r and dr dt. So the next part is we need to inventory what we have and see if we have enough information to solve this problem. So I'm trying to solve for this, so I don't have to plug in for that. I just have to solve for it. 2 pi, those are constants. R, well, we know that r is 38 centimeters at this point. And we know that dr dt, so that's the rate of change of the radius with respect to time. Oh, well, we know what that is. That's actually given here. So that's 6 centimeters per minute. So if I were to multiply this out, and I should have done this multiplication beforehand, that's going to be 360 plus 96. So what is that? 454? If I'm wrong, I'm sorry. 454. That can't possibly be right. 456 pi centimeters squared per minute. And that's step 4. Now, let's talk about a little bit about reasonability. Notice that this is centimeters squared per minute. Well, centimeters squared is what you expect for area. And since I'm looking for a rate of area per time, my answer may not be right, but if these units don't match, it's almost certainly wrong because of something you've done before. So keeping track of units can really help keep you stable and keep you from doing something kind of dumb.